Before I move on to examples 7, 8, and 9, I wanted to make sure that I fixed up example 6, since I had made a mistake in my answer key. The answer should be 1/2, and this slide shows all the algebraic work to do that. So first we are going to check, and we see that we have an infinity minus infinity scenario. That's an indeterminate form. So when you have infinity minus infinity, the recommendation is to get a common denominator. So in doing that, the first step was the common denominator of x minus 1 times the natural log of x. Then we're just going to simplify that algebra in the numerator a little bit. Now we evaluate the limit. We end up getting 0 over 0. When we get 0 over 0, we need to apply L'Hopital's rule. So we take the derivative of the numerator and the denominator. Don't forget, x, the natural log of x, needs to, we need to use the product rule. So here's the derivative of x natural log of x. All right, same thing happens in the denominator, minus 1 over x. Here we have a complex fraction, so I've made a recommendation to simplify the complex fraction by multiplying by 1 in the form of the LCD over the LCD. So that's x over x. When I do that, I eliminate the complex fraction. Let's evaluate the limit. We end up getting 0 over 0 again. That means we should apply L'Hopital's rule. And in the last step, applying L'Hopital's rule, we get 1 in the numerator. This is going to go to 0. This is going to go to 0 in the denominator. So we get 1 over 2. Okay, let's take a look at the other 4 examples. These are multiple choice answers, but in knowing what work to do is important just as well. So our first limit, we have 1 over h times the natural log of 2 plus h over 2. That's really the same thing as the natural log of 2 plus h over 2 all over h. And we're doing the limit as h goes to 0. Okay, so in the numerator we would get the natural log of 1. In the denominator we would get 0. That's a 0 over 0. So we're going to apply L'Hopital's rule. So that's an h. Okay, so we're going to take the derivative of the denominator, which is 1. We're going to take the derivative of the natural log of 2 plus h over 2. So that's 1 over 2 plus h over 2. Why don't we just automatically write that as the reciprocal? And then times the derivative of the inner mess, which is just 1. So that's what we have. So we have the limit as h approaches 0 of 2 over 2 plus h. Okay, evaluating the limit, we get 2 over 2, which is 1. All right, number 8. We have the limit of x cosecant x as x approaches 0. Remember, cosecant is the same as 1 over sine. So this is the same thing as the limit as x approaches 0 of x over the sine of x. Okay, so taking a look at that, evaluating that limit, we get 0 over 0. Applying L'Hopital's rule, the derivative of x is 1. The derivative of sine x is cosine x. Evaluating that limit, we get 1 over 1, which is 1. Okay. I'm going to go to number 9 on the next page. It's the same, just gives me a little more room. Okay, it says if f prime of x is cosine of x and g prime of x is 1 for all x, and if f of 0 equals g of 0 equals 0, then evaluate this limit. Okay, so the limit as x approaches 0 of f of x over g of x. Well, the first thing I do is evaluate the limit. So the limit of f of x as x goes to 0 is 0, and the limit of g of x as x goes to 0 is 0. So we should apply L'Hopital's rule. The limit as x approaches 0 of f prime of x over g prime of x. Well, f prime of 0, well, f prime of x is the cosine of x, so we can really fill in the derivatives with their functions, cosine of x and 1. And now we're going to evaluate the limit. That's 1 over 1, which is 1. Okay. Are you going to guess that D is the answer to number 10? All right, let's take a look and see. So here we're looking at the limit as theta goes to 0 of 1 minus cosine theta over 2 sine squared theta. Okay, so let's evaluate. We're going to get 1 minus, I'm recording, 1 minus 1 over 2 times 0, which is 0 over 0. So that means we should apply L'Hopital's rule. Okay, so the limit as theta approaches 0, the derivative of 1 is 0. The derivative of negative cosine of theta is sine of theta. The derivative of 2 sine squared theta will be 4 sine of theta times cosine of theta. Evaluating the derivative, the sine of 0 is 0. And in the denominator, we'd have 4 times 0 times 1, which is still 0 over 0. Let's do L'Hopital's one more time and see if this is all it takes. So the derivative of sine is cosine. The derivative of 4 sine theta cosine theta, I'm just going to pull that 4 out and do the sine theta cosine theta product rule. So that'll be sine theta times negative sine theta plus cosine theta times cosine theta. Simplifying a little bit, we're going to get cosine theta in the numerator. And here we have cosine squared theta, here we have negative sine squared theta. So cosine squared theta minus sine squared theta. That coefficient of 4 is still in the denominator. Okay. Oh, I'm doing a lot more work than I need to do here. Right? Did you see what I missed? What if I just cancel those out? We get the limit as theta approaches 0 of 1 over 4 cosine theta. Evaluating that, we get 1/4. So making sure you don't make algebra mistakes is important, because then you can just keep going and going and going. Eventually I should still come to a correct answer, but I'm doing more work than I need to. Okay, the answer was not 1. Thank goodness. And that is the end of L'Hopital's rule. Good luck.